So today I want to start on a new topic, which is the final kind of preliminary results that we need in order to develop the theory of statistical mechanics. And these are a few simple results from quantum mechanics. Okay. So if you have taken a quantum mechanics course, then these results should be familiar to you. If you haven't, then don't worry, because I will say everything that we need. Yeah, I will state the results that we need. The most important thing is that in a quantum system, as long as it's of finite size, the energy is quantized. That means the energy of a finite size system can only take a discrete set of values. So in any finite system, the total energy E can only take a set of discrete values. Okay. And we actually say that, in this case, energy is quantized, and this is what gives quantum mechanics its name, the fact that energy and other quantities only take a discrete set of values. So we say that E is quantized. If I draw this as a graph, if I plot the values of E of the system, it's not a continuum. So it's not a smooth line where the system can have any value of energy it likes. Instead, there are certain values of energy which are allowed and certain values of energy which are not allowed. And different systems will have different energy spectrums, but in general this is true. So the system can have this value of energy or this value of energy, but it cannot have a value of energy somewhere in between. Okay, this is what I mean by quantization of energy. Now, in particular, in this course, we're only going to look at very simple systems where the particles are non-interacting. The main example of this is an ideal gas. When we talk about the ideal gas, particles in a gas, we assume that they do not interact. We assume that, in a gas of oxygen, one oxygen molecule and another oxygen molecule do not interact with each other. They just pass through each other. So, for a system of non-interacting particles, we can simplify this. For a system of non-interacting particles, you can say that the total energy is just the sum of the individual particle energies. So let's say there are n particles. And the single particle energy levels I'm going to do is epsilon, to differentiate them from the total energy of the whole system. Where epsilon I are the single particle energy levels. And these are also quantized. So not only is the energy of the whole system quantized, but, well, necessarily from this formula, it follows that the energy of the individual particles in a non-interacting system is also quantized. If I plot the values of energy which a particular particle is allowed to have, it can have some values of energy, but not others. Okay? Again, EI is quantized. Now we are going to develop a theory of statistical mechanics based upon quantum mechanics. And here, the only thing you really need to know is what this distribution of energy levels looks like. The only thing we're interested in is, what values of energy are allowed and what values of energy are not allowed. And this will give us enough information to calculate the statistical behavior of the system. and therefore predict the thermodynamics. So, in particular in this course, we're going to be interested in 3 different kinds of quantum system. The first is just a non-interacting particle in a box. The second is the harmonic oscillator. And the third is what's called a rotator. And in each of these 3 cases, I'm just going to say what the energy levels are. So what values of energy are allowed, what values of energy are not allowed. And this is all the information we need. We don't actually care what the particular energy, what particular wave function or other characteristics are. Okay, so, as I said, we're going to do 3 examples of these single particle energy levels. And the first one we'll do is the simplest, and this is the free particle in a box. So we imagine we have a particle which is confined to move in a box of finite size, and we want to know what are the possible values of energy, in other words, kinetic energy, of this particle. It's free, so it experiences no potential, so all of its energy is kinetic. So the 1D case is very simple, so I'll actually do it fully in 1D. Okay? So suppose we've got a box of length L. So you have a one-dimensional box like this between 0 and L. Okay? And you want to know what values of energy are allowed. The critical formulas here is that the energy is kinetic energy, so I can write this as momentum squared divided by 2m. That's kinetic energy. But quantum mechanically, according to the de Broglie theorem, the momentum of a particle is equal to h bar times its wave number, where k, or at least the modulus of k, is equal to 2 pi divided by the wavelength, lambda. So the energy of a system is related to its momentum. The energy of a particle is related to its momentum, which is defined by its wave number, which depends upon its wavelength. So there are some conditions on what wavelengths are allowed. You impose some boundary conditions, and the most common ones are not what are known as periodic boundary conditions. Suppose I've got a wave inside this box. You demand that the phase at this point is the same as the phase at that point. So here the phase is 0, and here it's done a whole one wavelength. So it's gone back to the same thing. So this is allowed. And you can also have one which fits in twice, something like this. Now this condition quantizes the values of the wavelength. Okay? So only certain values of wavelengths are allowed. Therefore, k is also quantized, and therefore the energy is also quantized. So this is what are known as periodic boundary conditions. That's this condition like this. So what this tells you is that the length of the box must be an integer number of wavelengths. That's as I've drawn it. So this is the case n equals 1 in blue, and this is the case n equals 2 in red. We'll see it can be faster and faster. Okay? So here n is an integer. Now if this is a quantization condition on lambda, lambda is equal to L over n. This also tells you what k must be. K is equal to plus or minus 2 pi over lambda. So this is equal to plus or minus 2 pi over L times n. plus or minus because plus represents a wave, a particle therefore, which is moving in this direction. Minus represents a particle which is moving in that direction. So plus or minus just determines the sign of the momentum here. So either the particle is going this way or that way. Right. Therefore, k is quantized by this, because n is an integer. And therefore, finally, we get that E is quantized from this formula. So this implies that E, which is h bar squared k squared over 2m, should be equal to h bar squared over 2m times 2 pi over L squared times n squared. So, in conclusion, we get that epsilon is equal to, by this, 2 pi squared h bar squared over m times L squared times n squared. And I'll just put an n here to show you that the energy level depends upon the number n, where n is an integer. Okay? And the fact that k can either be positive or negative, I will put into the constant n, so I'll assume that n can either be positive or negative, corresponding to a wave going this way or that way. So that's the result. This is the quantization of energy levels in a one-dimensional box. Okay, and if I just plot quickly what these look like then, here I'll plot the energy divided by all of this stuff. 2 pi squared h bar squared over m L squared. That's just so it's an integer, right? So first of all, energy can be equal to 0, and there's just one state there when n is 0. Then when n is plus or minus 1, this is equal to 1, and I get two states, right? Because either n is plus 1, right? This is the n equals 0 state, this is the n equals plus 1 state, this is the n equals minus 1 state. The next one is when n is plus or minus 2, this gives you an energy of 4, and again you get 2, corresponding to the states where n is plus 2 and n is minus 2, and so on. So the energy levels in this system look like that. Okay. Well, this is true for a particle in one dimension, but really we're most interested in 3 dimensions, because we live in 3 dimensions. So we need to generalize this result to 3 dimensions. So in 3 dimensions, I'm going to consider a cubic box of side length L. In other words, I consider a box which looks like this, okay, and all of these lengths are L. Okay, so it's a cube. And inside of this cube, we've got some particles. Now in this case, K is a vector, Kx, Ky, Kz, and energy is h bar squared times the length of this vector squared over 2m. Okay. But the boundary conditions on each component of the k vector are exactly the same as in one dimension. In other words, the phase at this boundary here must be the phase same as the phase on the back of the box here. The phase on this side of the box must be the same as the phase on this side of the box. The phase on the top of the box should be the same as the phase on the bottom of the box. Okay? So those are the boundary conditions, and these give you a result where each component of the k vector should have this property. So this should be equal to 2 pi over L times nx, ny, nz, where each of these is an integer. So nx, ny, nz goes 0 plus or minus 1 plus or minus 2, and so on. So this is, again, the quantization here comes from the boundary condition. So again, periodic. Okay, so again, we get the result. If we just put this into there, we get the result that the quantization of energy, E, is h bar squared over 2m times 2 pi over L squared times the length of n squared and therefore I get energy which depends upon the vector n now, and this is equal to, again if I simplify, 2 pi squared h bar squared over m times, I'll explain this in a minute, v to the minus 3 over 2. V is the total volume of the box, times nx squared plus ny squared plus nz squared, the length of the vector n. Okay, and again, this is the result. This is the quantization of energy in 3 dimensions. So again, we can ask what do the energy levels of this look like. In 3 dimensions, they're quite much more complicated. So if I draw a similar picture as before, so up here, I'm going to draw the same thing. So this is epsilon divided by the constant 2 pi squared h bar squared over m v to the minus 3 2/3. That's just to give us a nice number. And I'll just draw what energy levels are allowed. Well, first of all, the lowest energy level occurs when all of these things are 0. Right? If this is 0 and this is 0 and this is 0, then the total energy is 0. So the lowest energy level is epsilon equals 0. And this corresponds to the vector 0, 0, 0, where all of the n's are 0. Next, I can make 1, an energy level of 1. How do I make an energy level of 1? Well, I need that this plus this plus this equals 1. Right? So either this one is 1, or this one is 1, or this one is 1. And if n squared is 1, then n can be either plus or minus 1. So in total, I get 6 energy levels here. 1, 2, 3, 4, 5, 6. I get 6 energy levels here, corresponding to the state 1, 0, 0, minus 1, 0, 0, 0, 1, 0, 0, minus 1, 0, 0, 0, 1, and 0, 0, minus 1. So I get 6 states there. I get 1 there. Okay? Now, the next one is when this thing can be equal to 2. Okay? The next one which is possible is when nx squared plus my squared plus nz squared is equal to 2. And I can do this, in fact, in 12 different ways. I can do 1 plus 1 plus 0, or 1 plus 0 plus 1, or 0 plus 1 plus 1. That's 3 ways. But then each of these can either be plus or minus 1. So that gives me 3 times 2 times 2, which is 12. Okay, so I won't bother to write them all down. But there are 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 levels corresponding to the case energy is 2 times this constant. Next is 3. The only way to make 3 is 1 plus 1 plus 1. But again, each can be plus or minus 1. So this gives you 8 levels here. 1, 2, 3, 4, 5, 6, 7, 8. Next one is 4. 4 is 2 squared. So I can get all of these levels like this. where 1 is replaced by 2. So again, I get 6 levels here. And it continues up, right? So you see that this is actually quite a complex behavior. The number of levels, depending upon the value of the energy, is quite a complex function, right? It goes 1, 6, 12, 8, 6. It's quite random. And we'll see that this is indeed a problem when we go to develop the theory of the ideal gas. We cannot solve it exactly because of this complex behavior of the levels. So instead, we'll solve it in some approximation where we don't count exactly the number of levels, but we make some average. Okay, so that's the 3D cubic, a particle in the 3D cubic box, and we'll use this one to develop the theory of the ideal gas. Right, so now the second example of a quantum system is the harmonic oscillator. So in this one, the energy, the Hamiltonian, but let me keep using energy, is given by, again, the momentum term p squared over 2m, and then there's a potential term which is a half m omega squared x squared. And again, we're in one dimension. This is a model of a vibrating spring. When you stretch the spring, it has a potential energy given by this, and at the ends of the spring, the moving masses have an energy given by this. So the quantized energy levels, I will just state the result. You will have seen it if you've done a quantum mechanics course. So the quantized energy levels are labeled by, this one is very simple. It's labeled by an integer n, and they are equal to n plus a half times the Planck constant times the frequency of oscillation. So here n is just a positive integer. So this one's very easy to draw. If I draw epsilon over h bar omega, then I get a level at a half, I get the next level at 3 halves, I get the next level at 5 halves, and so on. So the levels are evenly spaced in this system. And there's only one state per value of energy. Okay. Now the final system I want to describe to you, again, if you've done a quantum mechanics course, you will have seen the result is what's called a rotator. So the classical picture is very simple. I imagine I've got a stick which is fixed at one point and is allowed to rotate arbitrarily around this point. So the energy in this case is given by what's known as the moment of inertia, which tells you how the rotational kinetic energy is related to its angular velocity. So we'll say it has a moment of inertia, and the usual symbol for this is I. So we've got a system which is spinning, and it has a moment of inertia I. Now in this case, the energy is given by 1 over 2I times the square of the angular momentum. This is the result from classical mechanics. And if you've done a quantum mechanics course, you will know that the L squared operator, the angular momentum squared operator, has energy levels which are labeled by two numbers, which are usually given the labels L and M. and the energy in particular is 1 over 2I times h bar squared times L plus 1. So it doesn't depend upon m. M is just a counter of the degeneracy, which represents the size of the angular momentum around a particular axis. Okay, so that's what it is. And here, L is, again, a positive integer, 0, 1, 2, 3. And m is always between minus L and L. So m goes minus L plus 1, well up to L minus 1. So again, we'll draw a picture of the allowed values of energy, this time divided by the constant h bar squared over 2I. Okay. And these are given by L plus 1. So in the first case, if L equals 0, then you get energy 0. So you get one case, which is L equals 0, m equals 0. If L equals 0, then the energy is 0. And the only value of m is 0, so there's just one state. Next, if L equals 1, then the energy is, this gives you a 2. So the next one is at 2, corresponding to the case L equals 1. And here there are 3 possible values for m. M can be minus 1, 0, or plus 1. So you get 3 states here, 3 levels. Corresponding to this case, m equals minus 1, m equals 0, m equals plus 1. Then next, if L is equal to 2, then this is 2 times 3 is 6. And here m can be minus 2, minus 1, 0, 1, or 2. So that gives you a total of 5 levels. Corresponding to m equals minus 2, minus 1, 0, 1, or 2. So in general here, the number of levels you have is equal to 2L plus 1. If L is equal to 0, you get 1 level. If L is equal to 1, you get 3 levels. If L is equal to 2, you get 5 levels. So the general formula is that. Okay, so these are the only results, well, the only single particle energy level results we will use in this course. And ultimately, we're going to want to study the behavior of the ideal gas. And in order to do this, remember that I said if I've got an ideal gas which is diatomic, for example, then it has various different forms of energy. If I have a gas which is diatomic, first of all, the whole thing can just move. Right? The whole thing can just move. This is the case of a particle in a box. So this will be case number 1. Secondly, the molecule can vibrate. Okay, so this part can move in and out, and this part can move in and out, can vibrate. Okay. Now this we will model as a harmonic oscillator, which corresponds to the energy levels in 2. Finally, a molecule like this can rotate. It's a diatomic molecule, then it can rotate around its center like this, and this will correspond to the case of a rotator, which we've described the energy levels in 3. Okay. So by combining all these results, we'll be able to describe the theory of a diatomic ideal gas. Okay. The kinetic term will be the particle in the box, that's state number 1. The vibrational term will be the energy levels of the harmonic oscillator, number 2. And the rotational part will be these energy levels from a rotator. So this will be the kind of the final result in this course to describe theoretically the behavior of a diatomic ideal gas. So the final result that we need from quantum mechanics is upon the nature of multiple particle states. In statistical systems, you don't just have one particle, you have many particles, right? The number of particles is very large, 10 to the 20, for example, if you're talking about the amount of gas in a meter or so cubed. So the number of particles is very large, so as well as telling you the energy levels of each particle, I need to tell you how do these particles interact with each other. Multiple particles. Now in quantum mechanics, if I have two particles of the same kind, then they are indistinguishable. That means I can't tell them apart. So in quantum mechanics, two particles of the same type are indistinguishable. So we introduced this term last class, talking about combinatorics. It means that they can't be told apart. You can't tell which is which. So for example, if I have two electrons, I can't tell which is which. Okay? I can't say this is electron 1 and this is electron 2. They are indistinguishable. So in other words, it's impossible to tell the difference between two electrons. So in a gas, say in the gas of helium, I've got lots of atoms of the same type, and therefore they are indistinguishable. I have to treat each atom as if it cannot be distinguished from the other atoms in the gas. Particles in quantum mechanics come in two types, which are known as fermions and bosons, and the difference between them is how they occupy the energy levels, which I'll explain briefly. Okay. So there are two types of particles. Which are known as bosons and fermions. And as far as we know, these are the only two kinds of particles in the world. And what's different between them is their statistics when you try and put more than one particle into the same system. For fermions, you can only put in one particle per energy level. Only one particle per energy level. So once a particle has gone into that level, if I put another particle into the system, it can't go into the same energy level. It must go into a different one. But for bosons, we can put in as many bosons as we like into the same level. So as many particles as you like. Okay. Let me be more precise. Arbitrarily many particles can go into the same level. Arbitrarily. So that's the only, well, as far as this course is concerned, that's the only significant difference between them. So I want to illustrate this in some pictures. Suppose I've got a system which has energy levels like this, say 1 there, 3 there, 2 there. So this is 3 copies of the same system. And I fill it up with particles. So I could, for example, put one particle in this level, one particle in this level, one particle in this level, or I could put two particles in this level, one particle in this level, say. Or I could choose to put all of the particles into the same level, like this. Okay, so this is three copies of the same system, and I've supposed that my system has three particles, and I've told you what the energy level of each particle is. Okay? Now, fermions, only one particle is allowed in each energy level. Okay? That means this one is okay, because each particle is in a different energy level. But this one is not okay, because I've got two particles in the same energy level. And this one is also not okay, because I have three particles in the same energy level. Okay? So for fermions, this one is okay, but this one is not okay, and this one is not okay. This one is okay because they're all in different levels, but here they're in the same level. That means it's not allowed. This state cannot exist in a system of fermions. But for bosons, they're all okay. This is okay, this is okay, this is okay. I can put as many particles as I like into each energy level. Okay. And this difference will have some important implications which we'll talk about at the end of the course. So, this isn't very useful unless I tell you what kind of particles are fermions or bosons. So, let me now give you a brief list. Examples of fermions: a lone proton, or a lone neutron, or a lone electron are all fermions. Another example of a fermion is if I have an atom X, which has some atomic mass n, where n is an odd number. So, for example, if I take, there's an isotope of helium which has two protons and one neutron, this is a fermion. If the total number of particles in the nucleus is odd, then it's a fermion. Bosons, the most important boson is the photon, which is the particle of light, and also atoms which have an even number of particles in the nucleus behave like bosons. So atom N with n even. Okay, so again, an example of this is that helium-4, which is the most common isotope of helium, this behaves as a boson. So I've run out of time, and that's a good place to finish. So in this week, and in the week before the midterm exam, we introduced some probability theory, some results from combinatorics, and then in this class, some results from quantum mechanics. So starting next week, we're going to use all of these results to develop the theory of statistical physics. Okay? So that's the kind of main point of the rest of this course, so we'll start that next week. Okay. Thanks for your attention.